So what we're going to do this week is we're going to talk about where data comes from and what makes information data. We'll cover a little bit of what was in last chapter about the different forms of data. I have a different spin on it, and then I'll talk about how is it that you can examine it and look at it. So the first thing that we have to understand is that we're going to be using data as variables. And for us, a variable is any measured concept that takes on different values or can be observed with different values. So somebody just randomly shout out what they think might be a variable. One more time?
X.
Yes, X can be a variable. But what does X mean? Right, give me a variable. Mary Kate, something that varies by people. Your favorite color. Your favorite color is a variable. How do you know it is a variable? How do you know it varies? You think people are unique, but everybody knows that everybody's favorite color is blue. Universally, right? Who in here's favorite color is not blue? What's wrong with you people? William, what's your favorite color?
Black.
Why? Black's not a color. Okay. Any other reasons for your favorite colors? What do you got? What's your favorite color? You're wearing blue, so you like green? All right, Sparty on. Any other Spartans in here like green? No? Okay. What other favorite colors do people have? So far we have black, green, and blue. Red? Oh. What else we got? So you're lucky. You didn't know that for sure. You kind of thought maybe, sort of. Mary Kate lucked out, right? People do have favorite colors. It varies. Congratulations. Give me another one. Another variable, not favorite color. All right. Cars we drive. Anything else varies? Sport teams we like? Okay, let's get away from the superficial. Let's get into some real data. Age. Age varies. All right, height, weight. How so?
Well, not everyone makes the same income.
You lie. We all don't make the same amount of money? SES, socioeconomic status. You can use that for a range of things like education, wealth, income earned, debt. Okay. Anything else takes on different values that we can measure? One more, then I'll move on. Give me one more. There you go. Anything geographic, i.e. where you were born, where you live now. Okay. All of these vary. They can take on different values. So therefore, we can measure it, quantify it, turn it into data. It's now a variable. There are some things that you can measure that don't change. Right? They're called constants. Anybody give me a constant? A number that never changes. Well, 0 is always 0, but it's not a constant. No, actually, that does change. The hours in the day? Yes, that does change. No. It changes. Finish your sentence. The hours in a day on Earth? There you go. Because the number of hours in a day varies based upon what planet you're on. I need a real constant. Something that doesn't change. These aren't trick questions. That was a smart-ass answer, but that wasn't a trick question. Gender's not a constant.
You could say change is the
No, wrong class. It's not philosophy. And it's in the morning. I'm not that high yet. All right. What else do we got? A constant. A number that never changes. Nope. I mean, you could be right, but that's not what I'm looking for. You all know at least one. No. You all know at least one mathematical constant. Nope. You all know this number. The second I write it down, you're going to smack your foreheads and go, oh my God, I can't believe I'm that stupid. You ready? What's that? Pi. Pi is 3.14, blah, 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 blah. Why is pi a magical number? No. Why do we think pi is magical? Because pi is a number that never repeats in its, what do you call those, remainder? Right? There are mathematicians out there whose career it is to find the end of pi. When I was at Michigan State, a mathematician there set a world record for computing pi out to the 8 billionth decimal point. And it never ended and it never repeated. Pi is a magical number. But pi is always a constant. 3.1459 something. Okay? That's pi. It's a constant. A couple other things are constants. Let me think. Anybody ever heard of this thing? Einstein's theory of relativity. The energy of matter, or the energy of something equals the size of its matter, its mass, times the constant squared. Well, c is a constant. It's actually the speed of light. It's like 6 something to the 10 to the 8th power. It's really freaking fast. Just go with that. But the c in the equation is a constant. Constants are not variables. They're magical numbers. They never change. So we're going to be interested in variables, things that can take on different values, things that change, things that vary, hence the variable. Now, what shape we give these variables, in some regards, is up to us as researchers. So we can decide how it is we want our variables to change or vary. So what I'm going to do now is I'm going to go over 4 or 5 different ways we can measure. And then I'll address what the book calls measurement. And then hopefully we'll all be on the same page. So the best type of measurement of a variable for me is known as a continuous variable. And a variable is continuous if there is an infinite range of numbers available to complete that measurement. Okay. So in a continuous variable, we can go from negative infinity to positive infinity and anywhere in between. So think about this for a second. Let's name something that could be infinitely measured in a continuous fashion. Just think before you just blow out shout something out. What do you got? Better be good. Okay. So the argument is that the size of the universe is infinite. I'm halfway with you. How am I not with you? So the universe can be infinitely big, right? It can't be infinitely small. Or it can, but at some point it hits zero and it doesn't exist. So what does a negatively sized universe look like? That's a very good question, one which we are not going to answer in this class. So you get half credit for that one. What do you got? Same question. How can you have negative decimal numbers in pi? Try again. How so? Okay. I'll let you have that one. One question. When's it start? When's it stop? Isn't there always have to be a start to time? So if we go back, aren't we eventually going to hit something where there was no existence? I know it's early. But I'll leave it. I'll leave time. We can measure time in a continuous fashion. Does it actually have to have infinity on both ends? No, it does not. That's just me being a jerk. Right. But the best explanation for a continuous variable is one that goes from negative infinity to positive infinity. And since infinity itself is a concept and not even a real number, like we just knocked an 8 over and called that infinity. All right. There are very few concepts which will be infinite, both positive and negative directions. So we're already sort of going to bend the rules a little bit, but conceptually, we should be able to measure it for its full range of actual value. So something like time. Okay. Anything else that looks continuous, but might not be positive, negative infinity? Anybody got a wallet? What can I go digging around in your wallet looking for positive and negative infinity? Get a little better. Yeah, money, right? Can't we think about money in terms of positive and negative? And it's continuous, has a full range of value. The best thing about money is when we run out, we just print more. Numbers keep going, getting bigger and bigger and bigger. But can we have negative money? How can we have negative money? Yeah, we can have debt. We can absolutely have negative money. So you can measure it in both positive, in terms of income, worth, value, whatever. Or you can measure it in terms of a negative, which would be debt. How's debt represented in your wallet?
Receipts.
Close. How's debt represented in your wallet? It's not through your driver's license, but through your credit cards. Credit cards like instant debt. All right? You go to Sino Grill, you walk out, you're down $10. like automatically. Okay. Cash, positive. Credit, negative. All right. What else do we have?
Like in math, a line, you draw a line necessarily, the line is infinite.
In theory, which is what I did. Hence the arrows on the end. Yeah. Explain. We kind of set up temperature to be both positive and negative, right? Is there a infinitely hot point? Maybe. We don't know. Haven't found it yet. Not so good at physics. Is there an infinitely negative point or cold point? In theory, there's this thing called absolute zero. Anybody actually know why you can never achieve absolute zero? Right, so you can theoretically freeze matter so that the atoms and molecules in it stop moving. There's only one problem. How do you get colder than absolute zero to draw something down to absolute zero? You can't. So can we ever achieve absolute zero? No, but we can get really, really close and we can slow the molecules down. So absolute zero is an endpoint, but you can never get there. Because to make things cold, you need something colder to draw the heat and the energy away from it. So we'll get there. As close as we can get. All right, good. Good examples of continuous variables. There are things that are not continuous that we treat continuously. So we tend to treat things like age, even though they have a 0 point, as a continuous variable. At least we measure it as if it's continuous. So again, in theory, a true continuous variable goes from an infinite range of positive to negative, but in practice, sometimes we just have to go with the positive side. And then recognize that if you have a negative number, you've either coded wrong or predicted wrong or something is seriously screwed up. But the idea of continuous is you let it go positive, infinity, maybe to negative infinity if that's a possibility. Okay. Now I'm going to skip that. Another type of variable is known as a discrete variable. And this is one in which when we measure it, there's nothing in between the gaps. So between any two measured values is nothing. Let's think about age. How old are you? Okay. How old are you? Perfect. Is there anything between 19 and 20? Okay. There's not, Gregory? There's nothing between 19 and 20? You're either 19 or you're 20. I don't know. My kids aren't convinced of this, right? Because they're like measuring it down to the day. I am 7 and 246 365ths. Like, damn. Who taught you fractions? Okay. Age is not a good one. Because age, you can be 19, 0 month, 1 day. You can be 19, 0 months, 2 days. Right? There's actually 365 4-ish little units, depending upon a leap year or not, between 19 and 20. Now, we don't often divide things by 365ths, but it's possible. So age is not a discrete variable. It's just us being lazy when we ask somebody how old you are. But trust me, those halves or those approximations, they're important, right? Well, I'm almost 21. But you're not 21. So with a discrete variable, there's nothing in between those two values. So children, okay, let me see if I got this right. I have 2 children, Abby and John. I have 2 and only 2 children. I do not have 2.3 children. My cat is not a child. My dog, I don't have a dog. The people out there who say, oh, dogs are my children. No, they're not, because they're not children. Sorry, Mary Kate. You can make all the faces you want, but they're not kids. You can treat them as kids, but that's your mental health issue, not mine. Because my children are actually human beings that the state recognizes and makes me provide for. Okay? Whole children. Yeah, stepchildren are actually whole children. Okay? Your stepkid is still a whole kid. You may not be legally responsible for that kid, but it's still a whole child. Right? I grew up in a family situation where I had half brothers. Ed and Eric were whole people even though they were half brothers. Okay? Same dad, different moms. But they're actually whole people. Like real, for real, whole people. Okay? So what we have here is an exact form of measurement. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 students. Not really 20 because Mary Kate's not that good, but actually 21. I have 21 students in this room today. You are all whole people. Exact measurement. Now, forms of discrete variables can come in what we call nominal, ordinal, or dichotomous. And let me walk you through those 3 discrete variables. A nominal variable is a named category. When you see nom, think name. Nominal, name. We all have names. We all have first names and last names and some middle names, and sometimes we throw a hyphen in there. So let's think about religion. We can measure religion in named categories. Right? We're going to give Catholic a category. Raise your hand if you think you're Catholic. All right, congratulations. Raise your hand if you think you're Jewish. All right. Muslims? Buddhists? Shinto? Scientologists? Pastafarians? Methodists? Yeah, he thought about it. He's like, yeah, I'll admit to that. Lutherans? Presbyterians? Baptists? What the hell are you people? You making up your own religions now? Not religious. All right, I got a couple more there. Help me out here. Let's make your own. Non-denominational somethings. All right. How do I make this data? I can put everybody in a bin, but how do I turn these nominal groups into data? Easy. You just assign a number to them. All right, Catholics, what number do you want? Oh, I wanted you to say 3. Say 3. Why should Catholics say 3? Yeah. You believe in the Father, the Son, and the Holy Ghost. You guys get 3. Jewish people? Nah, 2. Muslim, 1. Buddhist, 7. Shinto, 5. Scientologist, 10. Right? The number just classifies the group. And it just represents what number group you're in. So we can turn categories into data by just giving it a number. That's easy. Now, what other things do you think are nominal forms of data? Give me another thing that's just a name, but it's something we might want to collect data on. No. Just a name. Race, yeah. We can treat race as nominal. What races do you want to exist? Can we just say white, because I don't know how to spell that? And I'm not from the Caucasus. I'm just going to write black. Let's simplify this. I know how to spell Asian. There you go. But Hispanic, well, what else we got? There we go. Yeah, we can do whatever. All right? We'll do Canadians. Why not? It's just a name group. All right. Give me another one. Political parties, go. That's not a party, unless it's the Independence Party. Reform. Baptist. Doesn't actually operate here, but close enough. You know there's a group called the Party Party? Whig Party. All right. We can go on and on. Basically, tell people your own political party. You can give it whatever name you want. There you go, your political party. And again, to turn this into data, all we have to do is assign numbers to it. All right, so that's nominal level data. There's really no restrictions on the groups other than you want to have enough groups that everybody should be covered. So how do we do that with race? Other. It's like, we don't know what to call you, but you probably got a good idea for your name, so we're just going to leave this other thing here and you can write it in. And you can put you are Cajun Canadian. Okay. Ordinal data, again, is discrete form of data. It has defined categories. But those categories we like to put into an order, hence ordinal. And we see these sorts of data quite a bit. Now you have to be careful, because you as a researcher, you don't want to be offensive and take something that is nominal and then go ahead and assign an order to it. So you don't want to go back and go, well, you know, Catholics are really the people that know God best, so we're going to give them 1s. And Jewish people would be Catholic if they just read the other book, so we'll give them 2. Right? And these other ones, well, there's a lot of Muslims, we'll give them 3. The Buddhists are peaceful. Shinto I know how to spell. And the Scientologists are all crazy, so we're just going to give them 99. Like, you have the very good potential to offend somebody when you start ranking religions. So don't do that. Don't assign something ordinal to data that should be nominal. You should be able to see a progression from one step to the next. Now, with an ordinal level data, again, we're saying that there's nothing between strongly disagree or disagree. That you're either a 5 or a 4. You can't come to me and say, well, I want to be 4.5. Because 4.5 doesn't exist. You either disagree or you strongly disagree. But what could you do as a researcher? Maybe not binary, but what are you saying? If I can't agree on these groups, what could I do? Add more, or what you were saying, simplify it and do less. Okay. So I could do I could do 3 groups. You either like it, don't care, or don't like it. And simplify it. Or I could make it more complicated. And I could insert more in here. Like, I'm on the slightly side. I don't want to say that I disagree with you, but I slightly disagree with you in the sense that I don't agree with you. Okay? I don't just strongly disagree with you, I hate you and want to kill you. Take it up a notch. So if we wanted to, we could add more categories in between them, but we got to go ahead and do that, and we have to do it on both sides. So if you can slightly disagree, you also have to be able to slightly agree. And if you hate it, then you have to say, I love that. So ordinal data, you can create as many categories in the orders as you want, but those have to be the options and the only options. So you have to sort of force people into these categories. Does that make sense? But you, as the person measuring it or creating the measurement, you control that. Now, the last type of variable is the simplest one, and this is known as a dichotomous variable. A dichotomous variable is usually also known as a binary variable, or my preferred term, a dummy variable. I don't know why we call it a dummy variable. You got to be pretty dumb if you don't understand it, I guess. With a dichotomous or a dummy or a binary variable, it's just the presence of a characteristic or a trait. On the wrong side of the room. On, off. binary choice. On or off. Are the lights on? God damn it. All right. So think of binary as a light switch. Now I just made it ordinal. All right. So being male, you are either male, thank you, or not male. Does being not male mean you're female? No. Thank you. All right. On, off. Having that trait makes it a 1, always a 1, never 100, never 1,000, never 27, always 1. Not having that trait makes it a 0. Off. Light switch on, light switch off. Now you can create a dichotomous variable from any other variable as long as you have what we call a cut point. Let me give you an example. Here's what I want you to do. In your notebooks, write down the age at which a person is old. What numbers do we have? 60. 75. Fuck you. 55. 65. Lucas? 60. Lorenz? Hmm? Yeah, you're lucky I didn't hear that. 1, 2, 3, 4, 5, 6, 7, 8, 9. I need one more. Anna? 60. 2, 4, 6, 8, 10. All right. Let's add these up. Oh, I lost count. All right, let's try this again. 55. All right. Our average is 57.9. Can we just round that up? Because I don't like fractions. Old is 58. All right. So at what point do you become old? On your 58th birthday. Once you hit 58, you're officially old, according to the 10 of you who came up with this idea. Is anybody in the room 58? All right. So old, not old. Is 57 and below. All right. We've taken a measure that we've said, sort of continuous, right? Age, close enough. It gets bigger. There's like up to 100 something, 114, 118. And we've said, yeah, but really, all the people over 58, they're all the same. They're just waiting to die. They're old. And so we've taken and created a measurement of whether or not you're old from a different variable. That's the great thing about measuring data, is when you create the data, you decide how you want to measure a concept. is there a way in which we could measure age in an ordinal fashion? Yeah. We just need to create the cut points. So at 58, you're old. At something to 57, you're middle-aged. You got a number? Kids suck. All right. So apparently 30 to 57, you're middle-aged. What are you from something to 29? 0 to 29? Oh, come on. Yeah, let's go with 18 to 29. You're young. And what are you when you're 17 or younger? Yeah. All right. That's better. We've taken a continuous variable, age, and we've turned it into an ordinal variable because there is a structure to this. Okay. Good. The book talks about this slightly different. The book talks about a nominal variable, we got that. An ordinal variable, we got that. And then for continuous variable, it differentiates between an interval and a ratio. A ratio is just a continuous variable that has a 0 starting point. How about an example of a ratio variable that starts at 0? Age is a ratio. Anything else? No, because we talked about you can have negative money. Speed. That's a great one. Good job. Shiny gold star for you. All right. Speed starts at 0. Unless you're going backwards. Can you be going backwards? Can't do negative speed, right? You can do it in terms of direction, like how close you are to the finish line. Right? Not only have I not started, I've actually gone the wrong direction. I'm further away from the starting line than when I started. I ran backwards. Or I just fell over and I fell a foot that way. All right, so that's a good one. I wanted somebody to say GPA or grades. Like, it's really hard to get a negative grade. Like, really, really hard. I could just be a jerk and be like, you owe me 10 points for making me read this test. Minus 10. But for the most part, grades usually start at 0. Your GPA is a ratio. Has a true 0 point. So it has these two, right? They talk about these two, which I call continuous. But then they leave out the best variable of all, which is the dummy variable. All right. How are we on measurement? Got the different types? Any concept that you can quantify, you also get to choose how you measure it. Measurement is a theory. It's a choice. All right. Seeing no questions, I'm going to move on. Now to actually what Chapter 2 is about. I'm going to go over what they talk about, which is how to examine data, and then I'm going to tell you why I think most of it's wrong. Because looking at data is one of those things where you have preferences, you have tastes about. The one thing I do like in the book is when it talks about tables, because tables are a great way to look at data. This type of table that I want you to know about is a frequency distribution table, also just known as a frequency table. F stands for the frequency, or the number of times, that data value is observed in the data set. The percentage is the percentage of the time that value is observed in the data set. The percentage should always add up to 0 plus or minus rounding error. So the F column, the number of times the data is observed. The percentage column, the percentage of the sample or the data set that value is observed. So this is from the book, and it's, I don't know, how do you choose the numbers in a lottery ticket? Do you do a random drawing? Quick pick. You walk in there and you say, I want to buy lottery tickets, but I don't know what I'm doing. Just give me lottery tickets so I can win the Powerball. And I don't want to fill out the sheet. Just give me some tickets. What they do is they hit the quick pick button and you get random numbers. And you might get 1, 2, 3, 4, 5, and your Powerball will be 6. But that's because you didn't choose. They just gave you random numbers. And you're in trouble. Because you're never going to win. And then you can come up with all these theories. My mom plays with the quick draw in New York, which is like Keno in Vegas. The idea that they play bingo every 5 minutes. Cannot convince my mom that the number 27 is a special number. Well, it's your birthday. No, Mom, it's just a number. They could be drawing letters, but that would limit them to 26. And they want to be able to draw this out as much as possible, so they go up to like 80. 27 is not a magic number, and contrary to what you believe, 34 and 44 do not always show up in pairs. You've found a pattern in something that is designed to be truly random. Stop. Just give me your $5 and I'll tell you whether or not you're a winner. Nope, you lost. You want to play again? Give me another $5. Yep, you won. Here's $1. Like, we can have that much fun playing the lottery when I'm the lottery. That's a frequency table. These are good. You're allowed to do this. This is a bar chart. You're not allowed to do this. The book says a bar chart is there to represent the frequency in which you observe something. What's the problem with this? Again, we're trying to represent the number of times you observe the frequency or the occurrence of a category. What's wrong with this? There is. They're right here. But you're close. What's wrong with this in conveying the information of the number of times an event happens? It's not exact. It is exact. Sequence occurs, okay, I go up and then I go over, and it's somewhere between 0 and 2.
Is it solely frequency or percentage?
You're getting warmer. That's true. But why is this bad?
Does it have something to do with the discrete variables?
Nope. It has to do with the fact that it's not this. So you have two ways of conveying information, and one is clearly better than the other one. Guess which one you should use? The one that is clearly better than the other one. Right? Because I know that the sequence method occurs exactly one time. Not somewhere between 0 and 2. If you've ever seen one of these, and you were asked to get information from it, I can guarantee that what you did on like a test question was you looked at this and you went, oh crap. How, right? Can I get an amen? When it would have been just so much better and easier if they just gave you this. And you don't have to go, oh, which one is it? Because that could be a 5 and it could be a 4. And I need a ruler. I got ruler panic. Like, I'm not sure if my line was actually straight. Bar charts are awful. If I want to know that random is used twice as much as pattern, what's the easiest way to know that? That 12 is twice of 6, or, well, this thing goes out to here, and this thing goes over to here. Is this as much as this much? Like, okay, well, let's double check. Okay, I go up to here, and then I do this again. You've all experienced this. I know you have. It might have been in 7th grade, but you all experienced this. This is horrible. Don't do this. Doesn't look good. Bad. Bad, bad, bad. No. Like, get a newspaper and whap it on the nose. And keep doing that until it stops coming around. It does not convey as much information as a table does. These things are even worse. Why are these bad? Pie charts. Stupid. No, for even more of a stupider reason. What doesn't this give you? The actual frequency. God damn it. We're trying to tell you how frequent something occurs, and we're not going to give you the actual number. Stupid USA Today with their pie charts. These are bad. Here's the thing. People aren't that smart. Like, they're really not. People are not that smart at all. And yet you want to take a number and turn it into area. I don't know about you, but I didn't do so well in the area of a circle land. Like, you got a couple straight lines, but damn, this curve. And that's why they invented calculus, by the way. So you can find the area under. Stupid. All right. So we're not going to do these either. These are bad. We're going to do tables. Why? Because tables give you the information that you need, and everybody can read a table. Now, 9 times out of 10, you just skip reading the tables, but you can, if you need to, use the tables. And then you have to shade them. You have to come up with, no. Apparently, the book thinks that it's good to combine a frequency table with another bar chart. And we'll call the bar chart a histogram, but it's still a bar chart. So you're still not allowed to do this either. Doesn't matter that they touch each other. These aren't good. Except, I'm going to walk that back. There's one way in which these are actually useful. And that's when we start talking about distributions and the shape of distributions. So you're not allowed to use a bar chart, but I will let you draw a histogram for one purpose and one purpose only. And that's if you want to try to figure out the shape of the distribution. But I strongly prefer that you just go ahead and draw the bar chart from the information in the frequency table. Make me feel better. So I'll allow this, if you have to. But you shouldn't have to. These are ugly. This is known as a frequency polygon. They don't do it for me. What they're trying to do here is just draw the distribution. But because we don't have a continuous variable, here we have a ratio level variable, they want you to say, well, these are really the bar heights. which they are. They're the bar heights. And we'll put them as dots and then connect the dots. Okay, so what you've done is you've drawn a sharp, pointy curve. That's what they're trying to do with this frequency polygon. Just go ahead and do a bar chart. Just go ahead. Why make it hard on yourself? Here's one of the main problems with relying on charts and tables, is that you have to follow a set of rules when you create them. Here's a bar chart examining the percentage of the sample that answered a question about partisan affiliation. Now the table, which is always best, tells us that 56% of our sample said that they were Democrat, 47% said they were Republican, and 52% said they were independent. Which doesn't mean anything to me because that's way more than 100%. So were you allowed to be like, check all boxes that apply? Well, I'm an independent Democrat. No, you're not. You're just a Democrat. So here we have the real way to do this, to represent. You notice that the real correct way goes from 0 to 100 on its y-axis. It shows the full potential range of values. This one here narrows down to between 45% and 65%. And because you do that, it makes it look like there's no Republicans out there. Geez, there's like, I don't know, 5 times as many Democrats as Republicans. Let me do my very precise measurement here because of my bar chart. Sorry, 4.5. I got 4.5 finger gaps here. This is a poorly constructed bar chart. They've taken information away from you. They've taken away the information that it should go from 0 to 100. So you have to be careful. That's why this data is always best. Not only do you get the full information in a precise amount down to the actual number, but you don't have to rely on whether or not the person who made the bar chart was an idiot or not, or was trying to trick you in some way by changing the y-axis. So, tables are best, unless you're trying to find the shape of a distribution. So in the last 15 minutes or so, I'll go through looking at distributions. Okay. Initially, we're going to tell you that understanding distributions is important because it allows us to find which value is the answer given most. That's known as the mode. So which value has the greatest frequency? If it has one hump, it has one mode. If it has 2 humps, it has 2 modes. It's bimodal. If it has more than 2, it's multimodal. What do we call a distribution with no humps? Yeah, I'm setting you up for a dad joke. It's a horse. All right. Unimodal, bimodal, multimodal. Just the number of humps, the number of most common values. It's one way in which we can describe this. The other thing that we look at when we're looking at a distribution of data is whether or not that data is symmetric or not. And so one of the first things I noticed about this class is that you guys are not symmetric. You guys are skewed to my right, which is why I asked that question. I wanted to sort of set this part of it up, right? So over here on my left, I got 6. Over here on my right, I have 9. You all are skewed to my right. Perfect up the middle. Good job. Symmetry is the idea that you are equal on both sides. Symmetry is the reason women wear makeup, which is to trick people into thinking your face is symmetrical, as if that is something admirable in a person. We use symmetry a lot as an aesthetic. We often do it with buildings. I went to university at a campus that the entire campus was symmetrical. This is the University at Albany in New York. It has an academic podium where when you walk in, you're actually in the basement because the podium is one level up. It's weird. And then the dorms were also squares, with each dorm had one high-rise 22-story tower in the middle of it. It's time to build the new library. Where did we have to put it? In the middle. Had to put it there because out front was a fountain. There's a little bus loop here. Man, it was really weird. Everything looked exactly the same. Because symmetry was an aesthetic. So the idea behind symmetry is that we get the same movement away from the mean, or the middle. Sorry, spoilers. We should be equally likely to observe this extreme value as we observe this extreme value. Basically, our whole semester of statistics is going to be built on this idea of a symmetric curve. We're going to really beat this into the ground. What you want to avoid, or at least you want to know, is whether or not your data is asymmetric. Is it skewed? Does it favor one direction over another? Now, how do they come up with this being positively or negatively skewed? Well, it's the opposite of what you would think. You don't look for the hump, you actually look for the tail. Because the fact that the tail comes out here means that there are more values in the positive end. Because if it were symmetric, you wouldn't have this out here. So the first tail here is in the positive end. So it is known as a positively skewed distribution. Whereas this is towards the negative side, it's a negatively skewed distribution. That always tricked me up. Tripped me up. Tricked me. So the shape of the curve tells us how the numbers are distributed around the center, which is typically a mode. We also can tell whether or not our data has a lot of variability in it. Now we're on to chapter 4. Variability tells us not only the size of the spread, but how likely it is that our data is to be spread out. If I were to poll this classroom, there would probably be not a lot of variability in the age of my students. Anybody in here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right, and here's where the fun comes. Anybody want to admit to being a minor at 17? 18. I got 1. 19. 20. We're getting there. 21. 22. All right. Anybody here greater than 40? All right. I'm not going. We're running out of time. All right. Our distribution is going to be peaked. It's going to be in this probably 18 to 20 something range. It's going to be in there. Since there's nobody 40 to 100, we just got a lot of dead space out here. So, not a lot of differences, you see a peak. Flat, I could go to a baseball game. And if I ask people their ages as they come through the gate, are you going to see 3-year-olds at a baseball game? Yeah. As long as it's not a thirsty Thursday, I'm not going to have a peak around 21 and 24. Right? I'm going to get everything from 3. Hell, I've seen babies at a baseball game, so we can start at 0. And I've seen some really, really old people at a baseball game. That distribution itself is probably going to be flat. From 0 to ancient. Ancient, like 90s. Pay attention to when they announce the birthdays at the Pelicans. There's like lots of times there's like, congratulations on your 92nd birthday, and you're like, holy crap. All right. What we want in this class is we hope that our data follows what we call a normal distribution. So this is our ideal. This is what we really, 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 really want. And if we don't have it, then we're just going to assume it. It's also commonly known as a bell curve. We think that in nature, we see a normal distribution in lots of strange and freaky places. A normal distribution is one that is unimodal, so it has one hump. It is symmetrical, so that hump gives us a dividing line where we could fold it on top of each other. And we would prefer that this distribution be neither peaked, which is narrow, nor flat, which is so wide. Like we want it to have a certain curve to it. This is going to be really important to us. Right? So we're going to have to sort of worship this normal curve throughout the semester, because we're going to use this curve starting week 5 on. And we're going to just have to be perfectly aligned with the concept of this curve. We need to understand that it's symmetrical. We need to understand that it should be centered at a certain point. There is an actual mathematical equation that will give you a curve. And actually, I'm not going to show it to you. Because if I show it to you, you'll freak out. Because I saw what happened when you freak out with the regression equation. But there is actually an equation that will create this curve. And we can, because we know how to create it, we can then mathematically tinker with it a little bit. Okay? All right. We're getting there. I'm going to do a video tomorrow on sort of where you would get data from. So that's what tomorrow's video is going to be about, and how to get it and look at it and manipulate it yourself. And I'm also probably this afternoon and tomorrow morning going to start grading the first section exercise. So if there's a question I have to grade, so don't freak out about your first score.